The crank OA of this mechanism rotates with a constant clockwise angular velocity of 10 radians per second. Determine the angular acceleration of link AB, the other one, and the acceleration of point B for the depicted position. Alright, so let's chuck a few things on this diagram to begin with. So first of all, we're told that this one here is rotating at 10 radians per second. So let's call it omega OA, since that's the ends of each of this link, and we know it's going to be 10. We're also told it's a constant clockwise angular velocity. So if you have a constant velocity, you have a zero acceleration. So that makes that easy. So we're going to be asked to find the angular acceleration of this other link. And if we assume our regular x, y, z out of page coordinate system, that's going to mean that if we assume this one's going in the positive direction, it's anti-clockwise. So alpha AB is what we're looking for. And because we're not given the angular velocity of this one here, we're also going to need to find it. Okay, remember that to perform your acceleration analysis, you need to know the angular velocities of all the different members within your system. Alright, so we can start this off. So remember that we're looking for this angular velocity and the we're looking for the angular acceleration of this link and the acceleration of this point here. But unfortunately, we're going to have to start with the velocity analysis. And we're going to do this so we can find omega AB, because we're going to need it in a second. So I'm going to consider the velocity of A relative to B, and I know it's equal to their difference in velocities, absolute velocities. So let's go through and find each of these terms individually. So the velocity of A relative to B, we can calculate from the fact that we have a rigid member joining the two of them. So it's going to be equal to omega for the member, which we called AB, multiplied by their relative radius. And if it's A slash B here, it needs to be A slash B here as well. So the angular velocity of this link is the thing we're trying to find. So I'm just going to write it with a K on the end in vector form. Remember, we've assumed it's the positive direction. And the radius of A relative to B, unfortunately, I think we have to draw a triangle to try and find it. So if we take out the triangle that sits in here, okay, we know it has a 45-degree angle. We know the length of this member is 225. This is point A on the corner, this is point B on the corner. We're looking for the radius of A relative to B. So that means we go from B back to A. So that's the direction of the arrow. But since we want it in terms of X and Y components, we're going to have to do the vector addition of the other two sides to get there. So the radius of A relative to B is going to be equal to this side, which is 225. The length is going to be the sine component, so sine 45j. It's going up, so it's positive, and this is going in the negative x direction, so it's going to be minus 225 cos 45i. So if you type that in a calculator, it ends up being simplified to 159.1j minus 159.1i for our relative radius. So this is what we can substitute in down here. Alright, and if we multiply out our unit vectors, we end up with this. Alright, so that's the first one of our three terms that we need to look at. So the next one is the velocity of point A. Okay, so for this one we're going to be able to use the fact that point A is connected back to point O through a member. So its velocity is going to be equal to omega for the member, which we called OA, multiplied by the radius of our point relative to the fixed one, so A relative to O. So now it's just a case of substituting in. We know omega OA is 10 radians per second and it's going in the negative direction. So this is going to be negative 10k. And the radius of A relative to O, we're going to need to take out a triangle. Again, we can take out just the one that sits in here. So it's going to be like this. We know this is a 60-degree angle, and this is where point A sat and point O sat. And the other piece of information that we need is the length of the member, and we're given it 75 millimeters here. So we can put that in. So we want the radius of A relative to O, so we need to start at O and draw our arrow back to A. But since we want it in X and Y components, it's going to be the vector addition of those two sides. So the radius of A relative to O is going to be equal to this side, which is 75, it's going to be sine 60 J, and then this side is going to be the cos one. Okay, and they're both positive because they're going in the positive Y and the positive X directions. So this simplifies to be 65 J plus 37.5 I. So this is what we're going to put in over here. Alright, so now we just need to multiply out our unit vectors again. So this simplifies down to be that. Alright, so we have one thing left that we need to determine, which is the velocity of point B. And for this one, we're going to be able to use the fact that we know that point B is attached back to, is able to move within the slot. Alright, so that's going to mean that if it's only able to move within the slot, the direction of its velocity is either going to be up or down the slot. I'm going to assume down, but it doesn't matter. If it comes out negative, you know it's the other way. So I'm going to call this the velocity of point B. And when we put it in vector form, we're just going to consider the fact it has a 15-degree angle in there to put it in X and Y. So if we draw the little triangle that sits in here, okay, so we've said this is the direction of VB. We knew it had a 15-degree angle due to the slot. So in vector form, we just need to work out these X and Y sides of the triangle. So it's going to be VB sine 15J for this side, and it's pointing down, so it's going to get a negative in front. And this is pointing the positive X direction, so it's going to be VB cos 15I. Alright, so now we're back to being able to substitute our three things here into our equation. Remembering that it was the velocity of A relative to B is equal to the velocity of A minus the velocity of B. So it's going to become, oops, it's a negative. Alright, now this is getting taken away, so all the signs are going to flip. Alright, so this becomes the equation that we need to solve. And remember that we have the ability to split this into I and J components, or two equations of I and J components to solve for our unknowns. And we have two in this case, alright, but we're only really interested in solving for that angular velocity. Unfortunately, this time we end up with I and J components tied up in both of the unknowns. So VB has both I and J's with it, and omega has I and J's with it. So it becomes a case of real simultaneous equations. So anyway, let's start with the I's. So we're going to get the following. Alright, so that's the I's for the equation. And if we take out the J's, Alright, so here we have an equation 1 and an equation 2 that need to be solved simultaneously. And this one we can kind of just solve a little bit easier by saying that both of the left-hand sides of these are identical. So that's going to mean that equation 1 can be directly equated to equation 2 by just saying these are equal. So that's going to mean that the right-hand sides have to be equal as well. Alright, so solving this out, if we get VB first, we can then solve for omega, which is the one we're actually interested in. So it was going to become 650 plus 375, swapping that one and putting VB's together. Alright, so VB becomes this divided by this, and that comes out to be 836.9 in millimeters per second. It's come out in millimeters because I took all my dimensions in millimeters. And just remembering back as a bit of a common sense check, we said that VB was down to begin with. It came out positive, as you can see, so that means that was the correct direction. If it had have come out negative, it would have been going back up the other way. So now we can find omega AB, and let's just take equation 1 here. So we know it's going to be equal to 650 minus, we now know VB, 836.9, and it's cos 15 on the end. So omega AB is going to be this number divided by this number, and it comes out to be about 1.00 rads per second. It's come out positive. That means it was the correct direction when we assumed it, which was positive. So it's going to be anti-clockwise. Alright, so we went through all of this so we could find omega AB. Now that we know it, we're going to be able to do the acceleration analysis, which should give us the two things we were actually looking to answer this question with, which was the angular acceleration of this bar here, and also the actual acceleration of this point on the end. So it's basically going to be a case of following this whole thing through again, except instead of looking at the velocity, we're going to be looking at the acceleration. So let's give this a go. Oops, cell. So this time we're finding the two things to answer the question, which is alpha AB and the acceleration of point B. So our starting point is to look at the relative acceleration that happens between A and B instead of the velocity this time. We're going to go through and find each of these individually again. So if we start with the acceleration of A relative to B, we know that they were connected by a rigid member. So it's rotating that member, so we're going to need to consider the normal and the tangential component of that acceleration. So if I just scroll back up, we're looking for what's happening between A and B. Okay. So between A and B and here, we know we have an angular velocity, omega AB, that we just worked out, and an angular acceleration of alpha AB that we're trying to find. So when we write this out, the normal component is going to be omega for the member, which was AB, multiplied by the relative radius, which is going to be A relative to B, again, since it's that form in the equation. And then this is going to be alpha for the member, which was AB, same radius. Alright, so substituting in, omega AB is what we just solved for. Alright, and we just worked it out to be 1 radian per second, and it was anti-clockwise, which is the positive direction. So let's just sub this in as 1k. And for these bracketed parts, you can often, if you've done the velocity analysis first, you should be able to go and find it in your velocity analysis. So if we scroll back up, we're going to be looking for omega AB crossed with r of a slash b. Whoop, try and find it. Here we go. So it's this here. Alright, so if you want, you can kind of take what you've already simplified it down to. We now know omega AB is equal to 1, so it's basically going to be negative 159I, negative 159J. So let's put that in. I'll just put the 1 in here. Alright, so that's what that ends up being. Alright, alpha AB is what we were trying to determine, and we drew it in the positive direction, so it just gets a K on the end. And we already worked out the radius of A relative to B. When we drew the triangles, we found it to be 159.1J. And minus 159.1I. Alright, so then it just becomes a case of expanding all of this out, and when you do that you get the following result. Oops. Sorry, alpha. Alright, so that becomes the first term in our equation. So next up we have the acceleration of point A. So going to use the same technique as we had before. We said that at point A was joined back to the fixed point at O, so that's what we're going to use to be able to solve it. So it's going to become the normal plus the tangential component of that rotation, and it's going to be omega OA, the angular velocity of the member. The radius is still A relative to O, the fixed point. This is OA and RA/O as well. Alright, so substituting in here, omega OA before, we were given it was 10 radians per second clockwise, so it goes in as negative 10. And again, we should be able to go and find where we solve for this bracket in the velocity analysis. So we're looking for omega OA multiplied by RA/O. Alright, so we've already simplified this down to be 650I take 375J, so let's shortcut it a bit. Put that in. Alright, and the other part of this is alpha OA multiplied by the radius, and if we scroll back up again, we can see that alpha OA is going to be 0 since we had the constant angular velocity, so that means we don't really have to do anything with this part. It's just going to go away. So simplifying this down, it just becomes this. Alright, so we only have one left, and that is the acceleration of point B. And again, we can use the trick for this that it's only able to move within the slot. So if it's only able to move within the slot, that means that the direction of the acceleration vector can only be in the direction of the slot as well. So last time we assumed VB was going this way. Let's assume that the acceleration of B is also going that same direction. So that's just going to mean we need to put it into vector form using the triangle again. So if we draw the triangle, we've said this is the direction of AB. We've got an angle in here of 15 degrees, so we just need to put it into X and Y parts. So it's going to be AB sine 15 negative going down, and AB cos 15I going to the right. Alright, so final step is just to put it all together. So we need to put in our original equation, this one here. So if you substitute in for each of the different things that you've simplified down, it becomes Alright, sorry, so this goes on to the next line since it's quite long. So we need to go through and find our two unknowns. We have the ability to split this equation into I and j parts again. So that's what we're going to go ahead and do. So on the I side, we end up with that equation there. And I'm just going to leave it like that for now. On the j side, we end up with that thing there. Alright, so all that's left is just to rearrange these two equations to substitute into each other. So if I go ahead and rearrange for the acceleration AB, I end up with that there. So this becomes equation 1, this becomes equation 2. So if you sub equation 2 into 1, you can solve. Okay, so the only unknown there is alpha AB, and if you rearrange for it, you end up with 36.6 radians per second squared. It comes out positive, which tells you it is anti-clockwise as assumed to begin with. And then substituting back into the equation for AB, the acceleration of point B comes out to be 1986. The units are millimeters per second squared, again because we measured everything in millimeters. It comes out positive as well, which means the direction we assumed is correct. It's going downwards in the slot. So the final answers for this question is that's your angular acceleration, and this is the acceleration of point B. So that's all there is.